Hello and welcome to the iRevise Supplementary Series for A-Level Physics. This is video 2 of the Astrophysics series. Most UK A-Level courses involve some sort of astrophysics. A lot of them have similar topics. There are some particular topics which are only focused on in particular exam boards. But what we will discuss in this video is cosmology, meaning Big Bang Theory. We'll talk about redshift. We'll just talk about how we've got theories of the universe and how we use redshift to figure out recession velocities, that sort of thing, how we calculate it. Okay, and then we have the Hubble constant, these types of calculations. We'll also take a look at using Wien's law. Okay, and I think some exam boards need you to know what the spectral class is based on temperature, based on wavelength, this sort of thing. I know some do, some don't. You'll see in the questions. We'll take a look at Stefan's law, luminosity, whether it's explicitly in your curriculum or not for your exam board. We will be looking at the inverse square law. A really good exercise would be for you to take Stefan's law and use that to derive an inverse square law. You'll see kind of how that works. Okay, we'll be taking a look at specifically angular resolution and telescopes when it comes to lenses. I know some courses cover lenses in greater detail than others. We will just be looking at what that means in terms of angular resolution and telescopes. We'll talk about parallax and that sort of thing. Okay, what we will not be covering, we'll do this in another video, we'll be looking at Kepler's laws, calculating the mass of a star, calculating the mass of a satellite, the universal law of gravitation, that sort of thing. That will be combined in with the video on gravitational fields, gravitation, and electric fields. Exam boards covered in this topic are Edexcel, AQA, the OCR Physics A and B, WJEC with some Eduqas, and the Cambridge Pre-U. So we've got a lot to get through. Let's get on with the astronomy. Okay, this is from the Physics A, the modeling physics paper, OCR, yeah, 2018. We've got a question here about the HR diagram. So the types of star here are going to be white dwarf. These ones here are going to be red giants at B. Okay, Sun is a main sequence star. Here's the surface temperature, maximum wavelength. Oh, we already know what kind of question this is going to be. Beta Pictoris has a maximum wavelength there. Calculate the surface temperature. Okay, now if we know that the yellow sun here, 550 nanometers, we see here that this is a shorter wavelength. So I'm thinking that's going to be more towards the blue. And because this ratio here is greater than 1, we know the temperature will be hotter. Yeah, I got a temperature of 8,221 or maybe 222 Kelvin. All right, let's look at our answers so far. Right, so white dwarf, red dwarf, that's what we did. We rearranged 86. Okay, so they've rounded 8,600. They like 3 sig figs for this exam board. Make sure you know your exam board. That's fine. Okay, and then mark the likely position of Beta Pictoris with a P. It's going to be hotter, and it's blue. It's got to, I'd say, somewhere around here. Right. On the main sequence and to the left of the sun. Yeah, so that's what we've got on the main sequence.
And still on the same page, we've got a cosmology question here. According to the cosmological principle, the universe is isotropic, homogeneous, and laws of physics are universal. What does homogeneous mean? Homogeneous is something which is the same all throughout, like if you have a glass of milk or something like that, okay? Everything is evenly distributed throughout the universe. That's what that means, all right? All right, so here we've got a question about absorption spectral lines. They tell us that the observed wavelength is 280 nanometers. They're talking about this funkily named galaxy here. It's 200 megaparsecs away. It has a massive black hole at the center. Calculate the wavelength of the same spectral line when observed from Earth. So what's the redshift going to be? They're telling us how far away it is. Assume the Hubble constant. Okay. So they're giving us the Hubble constant and the distance. We need to find out what the velocity is. So the Hubble constant is given in kilometers per second per megaparsec times 200 megaparsecs. So we're left with 13,600 kilometers per second is how fast this galaxy is moving. Just absolutely incredible. Okay. And then you've got this equation here now, where you've got this ratio. We want to find out what the observed spectral line would be. We need to find out what the redshift would be. Okay. So we'll take that 13,000, we'll divide by C, and we'll multiply it by the observed wavelength. I'm going to just keep it in nanometers, okay, because, and now C is not going to be just normally C. It's going to have to be in kilometers per second. So that's 3 times 10 to the power of 5 kilometers per second. And those kilometers per second will cancel out. That's a ratio of velocities. And we can just keep that in nanometers. That's fine. So I get a shift of 12.693 repeated nanometers. And if it's been red-shifted, it should be getting larger. So when we add that, we get a measured, I'll just round it to say 293 nanometers. State one of the characteristics of a black hole. It's extremely dense. It's a singularity. It's got all of its mass at one single point. Its gravitational pull, it's so dense that even light can't escape it. I think some black holes emit radiation because of the way some particles are kind of squished going in or something like that. I'm not sure. Let's see what they say. Okay, homogeneous, uniform distribution of matter. That's right. Here's our equation. We got, okay, again, 290. So I've added 13 plus 280, 293. It seems OCR, they'll accept that, but I think they're really big on 2 sig figs, so that would round down to 290. Okay? What did we say about black holes? We said they were infinitely dense. Light can't even escape. It's got a very, very high escape velocity. It's probably, better than saying light can't escape it, that's all right. You can say the escape velocity is greater than the speed of light. Okay, and here we go. It emits Hawking radiation. If you want to say that, that's fine. Distorts space-time, but you have to say significantly. It will bend light significantly. Okay? Yep, singularity. The physical radius is less than or equal to the event horizon radius. Okay, a bunch of things. There is a part C I've just realized. Let's see. The universe evolved from the Big Bang. Describe the evolution of the universe up to the formation of the first nuclei. Okay, this is interesting. This is different than other Big Bang questions we've seen. Okay, well, what we can say is we started off, all matter, whatever that was, started off at one single point here. It's extremely dense. There's a big explosion. We know that right after the explosion, there was a lot of energy, there was a lot of heat, things were very, very hot, but we didn't have neutrons, we didn't have protons, we didn't have electrons. These were made from other subatomic particles. This is a little bit out of the realm. I've not taught this side of this, the particle side of the physics course, and so I'll just jump to the mark scheme here. What would we say for 3 marks? The Big Bang was a singularity, very hot, right? There's an expansion. Yeah, don't talk about an explosion. We could say it's expanding, inflating. High energy photons, but there was no matter. Where did the matter come from? Well, first quarks and leptons form. You could talk about the quark-gluon plasma phase, whatever that is. Quarks combine, and so we know that quarks make up protons and neutrons. All right, and then we've got also hadrons. Hadrons are neutrons and protons. Nucleons combine to make nuclei. Okay? If you're getting into some detail there in OCR or your exam board, or maybe this is from a particle physics unit, you might need to know that. That's kind of an interesting crossover, isn't it? Okay, I've got a 2019, it's an OCR, Physics A, the modeling physics paper. Here we've got a comparison of 2 stars. We've got this star called TRAPPIST-1. It's an ultra-cool star, quite a low surface temperature. Look at that. We've got furnaces on Earth that are hotter than that surface temperature. Okay. Luminosity, it's not as luminous as well. It's not as much power. We're probably going to find the radius. We don't need to worry about these things. The temperature in Kelvin of the planet, D is the distance from the star, from the planet to the star, and L is the luminosity. Okay, we've got this expression here. All right, so the average temperature on Earth is about 290. Explain how life may be possible on some of the planets orbiting TRAPPIST-1. And then use your knowledge of luminosity to show the radius. Okay, well, I think if we wanted to find the radius, we would use the luminosity. We would have to use Stefan's law. Now, I think in order to do that, this area, I think we would need to find the radius. We need to find, well, that's where you're going to get your radius. So in order to do this, well, we could do this bit first if you like. Okay, so I've got 2 times 10 to the 23 divided by Stefan's constant divided by, this is very sloppily written, 4 pi, and then I've got 2,500 to the power of 4. I get 7.186 times 10 to the 15 for r squared. So that means r is going to be 8.4, let's say 8.5 times 10 to the 7 meters. If we want the surface temperature of a planet orbiting TRAPPIST-1 to be about 290, we can use this formula here. We'll take that these temperatures are the same, and now really it's just a ratio of distance squared to luminosity. So if we put little t subscript and our little sun subscript, you put an s there. I like to use the old-fashioned symbols. Okay, and what will we have? Well, I want to know what that distance would be. So the distance is going to be the square root of the distance from the sun, and then we're going to end up with a ratio of luminosities here, aren't we? And we see from that ratio of luminosities, we're lowering that number there, aren't we? We see from that ratio, the sun's luminosity is higher. We've got a smaller number now, okay? I get an answer here of 3.44 times 10 to the 9 meters. That's much shorter than 1.5 times 10 to the 11. So 3.44 is it's a little over double 1.5, but because it's 10 to the 11 and this is 10 to the 9, you know, it's 100 times larger, but then there's this half factor. So it's 50 times the distance. Not quite, almost. So there is between 1.6 and 9 times 10 to the power of 9. So this falls within a Goldilocks zone. That's fine. Okay, we've done some calculations. There's more that you could do some writing if you wanted. But what do they want you to talk about? What do they want? Okay, so we've done some calculations. Explain how life might be possible. Well, yeah, a smaller radius, we've said, but it is also cooler. And so because it's a cooler and this radius is smaller, this planet can get closer to it. It is possible, maybe, if a planet were to be somewhere in that zone, is it likely that a planet will be exactly at that same distance to allow for a temperature of 290 at the surface? I don't think so, but we do have a range. And if we're within a range, that's fine. Now, what does that mean? Does that mean we're going to get, liquid water on the planet? Yeah, maybe. I don't know, if the elements are there. Does that mean we're going to have an oxygen atmosphere that would sustain life? Will we have something like a carbon cycle, carbon dioxide, oxygen exchange? Are these life forms breathing nitrogen instead? I don't know if there's even life on that planet. But, the thing is for us to live there, life for us, we would need, does it have oxygen? Okay? I'm not sure what else they're looking for with the 6. Let's go take a look at the mark scheme. You get correct calculations for radius and temperature, range, or distance, or intensity of Earth-like temperature. Just some calculations. There's a well-developed line of reasoning. So you need to actually articulate what you've just done. You can't just do the calculations if you want the full 6 marks. What could we explain? Well, we know it's cooler than the sun, but the planets are closer to this star. Okay, possible for temperature and planets to be like, it is possible. We've calculated that. Okay, we showed that. All right. For life to exist, temperature is not the only factor, so you could talk about that. I mentioned about, well, what kind of atmospheres do we have? Is water around? That sort of thing. Okay, you could have calculated what the constant was when they gave you t to the 4d squared over l at some constant. You could have done that. But I mean, we just set one planet to the other. That's fine. It's a constant. I mean, if you did that, you get credit for it. We didn't do that, but that's fine. We went and calculated something else. You could have put these 2 different distances into the equation and found out the respective temperatures. Okay, and we could say, hey, we're between 180 and 430 Kelvin. We would need something somewhere in between. This is the furthest planet that we know of that's there. Too hot, the closest one too cold. Is there a planet somewhere in between you could talk about? Goldilocks zone kind of thing. There must be a planet with temperature similar to Earth, yeah. So, if there's something in between, okay, but who knows? We've used this to calculate the radius, yes. Or L over T to the power 4 is smaller for, you could compare that between the 2 suns. There's a bunch of the comparisons you can make, comparison of calculated intensities, yeah. So, I don't know, I feel if you were to just explain kind of what we were saying based on those calculations we did, it seems it's good for 6. But these are the types of questions you want to practice and really nail. Okay, I've got a paper 1 of the Physics B from OCR, and this is from 2019. Okay, in part B, it's believed there's a black hole at the center of our galaxy, which is 26,000 light years away. And the orbits of several individual stars around the black hole have been determined. There's a figure here which shows the orbits of 2 stars. The plane is perpendicular to the line of sight. So it's a top-down view. It's not what we would see. Okay? S1 is nearly circular. S2 is elliptical. Show that the radius of the S1 orbit is more than 2 times 10 to the 14 meters. We've got a light year here. Okay, and we see here we've got the angle is in microrads. We see that if I go from -1 to 1 there, so this plane is perpendicular to the line of sight, which means we are looking at it straight on. You could say there's a distance here. That's the angle.
It's parallax.
We're looking at that. This angle here is, it looks to be like it's 1 microrad. We are told it's 26,000 light years away. 26 kilolight years. And so what is this distance here, yeah? So x over 26k. All right, so we'll just do sine of, now you got to be careful, 10 to the -6. Be very careful you're not putting in, when you're changing your microradians here, be very careful that you're not taking, say, typing in your calculator something like 10 e -6, because that's actually going to give you 10 to the -5. You got to watch what you're doing. Anyway, times 26,000, so I get 0.026, and of course you need to multiply that by the conversion factor to make that into meters, and I get 2.47 times 10 to the 14. So that's about 250 trillion meters, okay? You know that sine theta is equal to theta at such a small angle, so you really could have just done x over d, and that would have worked as well, I think. Okay, and so we had figured out what that radius was. We got that. Like I said, you can do either using tan or sine or even just theta, because it doesn't matter. Okay, moving on.
This is paper 3 from Cambridge Prep U, and it's another question on sun surface temperature. Use Stefan's law to find the luminosity of the sun. Here's the radius. There's the surface temperature. In here, use Wien's law to calculate the peak wavelength. This is the constant they want you to use. State the color. I think I don't want to clog up the video with, a lot of step-by-steps on these very repetitive questions. Why don't you pause it, take a look at these numbers, do the calculation, and we'll have a look at the answers. Okay, so there's your Stefan's law, and there's your answer, and then from Wien's law you got that. What is that wavelength? I guess you need to kind of know what that is. I do happen to remember that 550 nanometers, that's supposed to be those yellow sodium lines. Maybe that's a little shorter than 550. So maybe green is a good estimate, yeah? Moving on to part C here. Use a relationship between mass and energy to calculate the rate of decrease of the sun's mass. Okay, remember that units for luminosity is watts, and so that is actually a unit of power. What is it, 364 times 10 to the 26. So what's happening is losing 3.64 times 10 to the 26 joules per second, and they want to know what mass per second that is. Well, that should be equal to a certain amount of mass times the speed of light. So if we take that 3.64 times 10 to the 26 and divide by the speed of light squared, that gives me 4.04 times 10 to the power of 9, looks to me kilograms per second. Okay, yeah, and there we go. So that's 4 billion kilograms per second. Okay, on the same paper, they do this thing where they mix a bunch of different questions together. We got talking about particle physics here. We got line spectra, some more quantum theory with standing waves. And then we get into this part E here, talking about the fusion of hydrogen. So Betelgeuse is older than the sun and is a red supergiant.
Beetlejuice. Beetlejuice. Beetlejuice.
It's showtime.
Okay, and let's see. So they give us the radii, and they give us the temperature. Okay, just as each other. From the information, determine the ratio of the luminosities. Okay, so we know luminosity equal to Stefan's law. Okay, so if we set this up, LS over LB, we know that the constant's going to cancel out. We know the area is 4 pi r squared. The 4 pi's are going to cancel out. We're going to be left with rs squared over rb squared times ts to the power of 4 over tb to the power of 4. Now, if we look at what we've been given here, we see that rb is the same as 400 rs. So we'll eliminate that. Okay, if we plug that in on the bottom, we'll get 400 squared rs squared. The rS's are going to cancel out. Okay, and then up on top here, we see that the surface temperature of the sun, okay, it's double what it is on Betelgeuse. Betelgeuse is a red giant, so it's a cooler planet. So we're going to have to plug that in. That'll be 2 to the power of 4 TB to the power of 4. The TB's cancel, all right? And so what are we left with here? We're left with 16 over 16 with 4 zeros, so 160,000. Looks to me like our ratio is 1 over 10,000, or 0.0001. If we take a look at our answer, yeah, 10 to the negative 4, 1 over 10,000. I think we've got it. Next, I've got the paper 3 and section B. The Astrophysics from the AQA 2017. Draw a ray diagram for a Cassegrain telescope. I can't draw on here, but I can at least show you a picture. Let's see, your diagram should show the path of 2 rays initially parallel to the principal axis as far as the eyepiece. And of course, the mark scheme's useless because there's no actual diagram. It needs to have both mirrors correct, 2 rays correct. So what does that actually mean? I'll show you. Here's an idea. You can see here you've got a concave mirror. As we saw in the other question, it has a parabolic surface. It will reflect off of a convex mirror, and that will allow for an image to be formed on an eyepiece. I don't like this diagram because I don't think it's going to go like this. It's going to be more likely that they're going to cross over and then go through the eyepiece like that. Okay, but here's an example. Here's another example. So parallel to the primary axis, reflecting off of the mirror, and then going through, something to that effect. I think that ticks all of those checks there. That's fine. You could read this a little more here. First mark is for the concave primary mirror and convex secondary. Primary should not look like 2 mirrors. So I imagine you want some sort of continuity in how you do this shape so that it's 1 mirror with a hole in it. Okay? Condone a flat secondary, but you got to label it convex. Okay? Do not condone a concave secondary. It won't work that way. The second mark is for if the 2 rays that are initially parallel reflected and then they cross. They have to cross, okay, as they pass through the primary. Ignore arrows on the rays. No lens needed, but ignore the rays after the lens if drawn. So if you don't draw the lens out here, the eyepiece, that's fine. You don't need it. You do need to have them crisscross here, it seems. Okay? And they're not worried about the arrows, but poorly drawn rays, you might lose a mark. So just be careful. It's only 2, so watch it. The Kielder Observatory in Northumberland includes 2 optical telescopes attached to the same mount, so they can be used to view the same object. Some of the properties of these telescopes are summarized in Table 1. Okay, suggest which telescope produces a brighter image. Well, the one with the larger diameter, it's going to be able to collect more light, and so it should have a brighter image. That's what I would say. The only thing I can think of mathematically would be that if that's your diameter, that you're going to have a much larger d squared. That's going to be 160,000 as compared to 4,900. Okay, it's going to be much, much larger. Let's see what they say. Okay, it's going to be B is brighter with support. So what would you say? The brightness is related to the d squared or to the area. You could do a calculation of the areas or d squared. Okay, I guess you get a mark for actually doing that. Okay, it says an unsupported answer gains no marks. Okay, so you can't just say it's B. You could say B's got a greater area or a greater diameter, but I think, I missed this. Support your answer with a suitable calculation. So 1 mark. So yeah, show the calculation then. The minimum angular resolution of a telescope can be determined using the Rayleigh criterion. Explain what's meant by the Rayleigh criterion. The Rayleigh criterion is the generally accepted criterion for the minimum resolvable detail of an image. Okay, and this is your formula. Okay, so you could mention something like that. You could write something like that. What do they say? They're talking about correct diagrams can gain both marks. Those of you in the AQA, maybe you've got diagrams to sort this out. I'm wondering what they're talking about when they say coincides with central maximum. Center of the airy disk. If they're talking about central maximum, that seems like a diffraction kind of thing to me. And that's in a different video. 2 objects which will be resolved when the first minimum of the edge of the airy disk in the diffraction pattern. That seems like a diffraction question to me, so I'm not entirely sure, but you know, maybe those of you in the AQA have a better idea about that one. Discuss which of the 2 telescopes would be better at resolving the images of 2 objects that are close together. Okay, so I'm not sure if we're just assuming that the wavelength's the same for both, but I think we clearly see there's a proportionality. It's 1/d. So if you have a larger diameter and you divide by that, you have a much, much smaller angle of resolution there, and therefore you should get a better resolution. What would they say here? B is better because it has a larger diameter. The minimum angular separation or angular resolution depends on 1/d. Yeah, okay. No mark for an unsupported answer. You can't just say B. B first is for arguing B is better due to the large diameter, and then say why does the large diameter matter? Because it's an inversely proportional relationship, something like that, or it's inverse to the angular resolution, that kind of thing. Okay. Correct calculations can gain both marks using any wavelength. I would just assume that if you are going to make a comparison, you would use the same wavelength for both because they both seem to be using light. Okay. On to number 3, we've got 4 stars in the constellation Hercules. Again, we can see the spectral class, we can see the apparent magnitude, and we can see the distance. Define the parsec. What is a parsec? It's about 3.26 light years. A parsec is actually a unit of length, not a unit of time, so some people get that mixed up.
Han Solo. I'm captain of the Millennium Falcon. Chewie here tells me you're looking for passage to the Alderaan system.
Yes, indeed. If it's a fast ship.
Fast ship? You've never heard of the Millennium Falcon?
Should I have?
It's the ship that made the Kessel run in less than 12 parsecs.
Right, the definition of a parsec is going to be this distance here or this distance here, because when you get such a small angle over in this area here, the hypotenuse and the adjacent side end up being the same, and this is why tan theta approaches sine theta. They end up being kind of the same. But that length comes from, okay, it's the angle. It's when the angle subtended is 1 arcsecond. When you've got a distance here opposite to that angle of one astronomical unit, then these distances here are 1 parsec. Okay, what is an arcsecond? Well, you'll remember that there are 3,600 seconds in an hour, and as such, there are 3,600 arcseconds in 1 degree. That's how that works. Okay, so that's what an arcsecond is. It's 1/3,600th of a degree. So something to that effect. I'm sure if this is in your syllabus, you know how to answer this. Deduce which star is larger, Corniforus or Rutilicus. Okay, they seem to have the same apparent magnitude, same spectral class. All things being considered, they should have the same brightness, okay? But one of them is further away. It's further away and still has the same apparent magnitude. I would therefore say that Corniforus is larger. Let's check in with what they say so far. The distance at which 1 astronomical unit subtends an angle which is 1/3,600th of a degree, okay, right? Or you can say an arcsecond if you like. That's fine, okay? Draw a diagram if you need. That's okay. You can draw a diagram, okay? Why? Okay, so what did we say? What did we say on that star comparison? We said they got the same spectral class, therefore they have the same temperatures. They have the same apparent magnitude, but K is significantly further away. Therefore, K, this Coniforus, must have a greater power output to be viewed as the same apparent magnitude from so far away. And as you know here from Stefan's law, if you to have a greater power output, or a greater luminosity, some exam boards put an L, this one puts a P. Okay, in order for it to be greater, okay, having the same temperature, it must have a greater area, and therefore it's bigger. One of the 4 stars has its peak blackbody radiation at 1 micrometer. Okay, calculate the corresponding temperature. Well, this is Wien's law, and we're just going to rearrange. This is the constant here. We're going to divide by 1 micrometer, which is 10 to the negative 6, and I think you'll see that that's going to give us 2900 Kelvin. Okay, explain which star produced the blackbody radiation curve described in question 3.3. Okay, so which star would have done that? Okay, well, we need it to be, let's get back to our spectral class. Okay, so 2900. 2900 looks to me like an M star, quite a cool star. And we see here that the one with the M must be this Rassel-Gethy. Okay, so that's what I would say for 3.4 Rassel-Gethy, because it's M class, it's got that temperature range. It seems to me in the AQA they want you to know these classifications, unless that's in a data sheet I'm not aware of, but I don't think it is. Which star has the brightest absolute magnitude? If you take a look at the apparent magnitudes, they're all very similar. And if you think back to that equation, if you think back to this equation here, okay, with all of these apparent magnitudes being kind of the same, so let's rearrange this. So I'll put M on this side, and it'll be little m, which is the apparent magnitude, subtract 5 times log d over 10. Okay, if you take a look at this d over 10 here, right? The distances, they're all double digits except for Rassel-Gethy. And I think if you do 110 over 10, that's already 10. You do log 10, that's 1. You're going to be subtracting 5. So whereas these other ones, this is going to be log of 1. This is going to be, these are smaller. You can see how that's going to fit into this equation. And so this absolute magnitude, I think, is going to be the most negative once you put a number in here. So my guess is Rassel-Gethy. And then they want you to determine the absolute magnitude of Saturn. So Saturn's got a distance of 23 and an apparent magnitude of 3.1. So we can just plug these in here, 3.1. This was 23, so it's log of 2.3. So 3.1 minus 1.8. I get about 1.29 for the absolute magnitude of Saturn there. Okay, so there we are. Yeah, 1.3. That's all good. 3 marks. We've plugged it all in. That's good. Pause if you want to read about the mark distribution. That's fine. We were right about Rassel-Gethy. I think our reasoning was sound. We also talked about it being the only spectral M class, and so that's the one as well. It's the one here that we got the 2.9 times 10 to the 3, or 2900 Kelvin for. Yeah. So that's all good. Let's get on to number 4 here. They want you to do a sketch of a light curve for a typical 1A supernova, absolute magnitude versus time in days. Here's the typical graph. This is, again, maybe something that you need to know for AQA. Here's a type 1 supernova template. It's got absolute magnitude here on the side, and you can see it goes out in days. Looks to me like the peak happens here at 0 days. So I would imagine our graph looks something like that. Again, these mark schemes aren't very helpful. The first mark's for the scales, second is for the curve, third is for the value of the peak. Okay, so you've got to add some, it says here, label the axes with suitable scales. Okay, so as we said, the peak needs to be, I would just refer to something like this. I don't know what they expect you to know in AQA, but here you are. Okay, so they say absolute magnitude scale is getting more negative going up, and the time scale with 0 along the axis going up between 10 and 400. Line drawn going up and down, with the left hand steeper than the steepest part of the right hand. So what they're talking about here is you can see that the gradient here is steeper and it's more stretched out on the right side. It's a little more shallow. And a line drawn increasingly quickly with a suitable peak, absolute magnitude between -18 and -20. So again, this is very specific. I'm assuming this is numbers you need to know. You can see on this graph here, they've got -19, -20. They're going to give you on yours, on your question over here, they're going to say between -18 and -20. So make sure you know what you need to know for your specific exam boards. Explain what is meant by a standard candle. It's just something that we we can compare brightness to, and apparently a Type 1a supernova is used as a standard candle. So it's just something we can, compare. Measurements of Type 1 supernova in 1999 led to a controversy concerning the behavior of the universe. Describe this controversy and how the measurements led to it. I don't know anything about this one. I'm just going to go jump to the mark scheme. Before we answer that one, a standard candle is an object whose absolute magnitude is known, and therefore it can be compared. So probably my answer wasn't the best.
Oh, the ego on you.
It's better to say it's something whose absolute magnitude we know, and then that's how it's used as a comparison. Okay, you can talk about inherent brightness, luminosity, intrinsic. It's predictable. It's not fixed. It's not fixed or constant because it could change, but it's something that's predictable at least. Okay. Anyway, moving on with what happened in 1999 there. Measurement of supernova do not agree with predictions from Hubble's law. So the universe must be expanding at an increasing rate. Hubble's law tells us that the universe is expanding at a constant rate, but it seems that according to this, it was going at an increasing rate. Okay, we don't know why this is. No known energy source for this expansion. We don't know. That's the theory of we get this dark energy, this dark matter, which might contribute to that. Okay, so hopefully you can get this one. Number 5 is a nice little 6 marker written answer. According to NASA, nearly 2,000 exoplanets have been discovered by 2016. The aim is to find an Earth-like planet orbiting a Sun-like star. Discuss the difficulties associated with the detection of an Earth-like planet orbiting a Sun-like star. Okay, well, in your answer, you should compare the methods that are used in search and suggest what is the most successful. Have a go at this yourself. Even if you're not an AQA student, I'm sure you can come up with some methods. I'll give you a hint. There should be 3 of them. So have a think about what they might be. I think an obvious one would be the mutual orbit around a center of mass, and you might see some Doppler shifting. You might see a planet moving in front of a star, much like this is how the moons of Jupiter were discovered. We saw them transiting across Jupiter, and Galileo was able to determine that there's moons. Okay, because the brightness of Jupiter dropped. It would be the same type thing. Let's see what else they've got here. So transit, like I was just talking about, dips in brightness as a planet crosses in front. Okay, alignment must be correct. We have to be in the plane of the orbit, so it might not be possible depending on how these, where they are in relation to Earth. Okay. Earth-like planet could be observed if it's not too far away, because it'd be able to, we'd see the difference in that light there. Okay, a radial velocity, right? So when it's spinning around, like we say, you'll see a periodic shift as the star's moving away or towards you, depending on where you are in its rotation. With this, the planet's mass is much less than the mass of the star, so it would be a pretty slight effect. But you might be able to detect the planet still, and then you could just have a direct observation. Direct observation is probably very unlikely. It's a little bit too far away. It's too small. It says here it might be too near the star and too cool to be detected. Okay, against the brightness of the star. Yeah. Okay. So I'm not sure how you squeeze 6 marks out of there, but you're going to have to do your best to practice. They say here all 3 methods described, all 3 methods applied to Earth-like planets, judgment reached. Okay, that's basically it. Say the method, talk about how it might work, and then say, do you think it's possible? Could that happen?
Well, it certainly looks like a lot of words.
Okay, and this is a Component 2 paper from the WJEC Eduqas. And this is from 2018. Astronomers analyzing the wavelengths of the dark lines in the line spectrum of a distant galaxy note they're increased by 16% compared to their normal wavelengths. Why is there an increase in the wavelength? Well, this is a redshift, isn't it? This is a redshift. This is a redshift due to the expansion of the universe. Okay? Calculate the distance of the galaxy from the Earth. Okay, well, so our redshift is 0.16, isn't it? The change divided by the original, and we know that should be equal to. All right, so what's it's just going to be 16% of the speed of light. which is 4.8 times 10 to the 7 meters per second. Okay, that's the velocity. What's the distance? Okay, if you remember here, we're going to have to take this velocity and divide by the Hubble constant. Eduqas data booklet tells us that the Hubble constant is 2.2 times 10 to the negative 18. Okay, so the distance that this galaxy is away from Earth is, are you ready for this? 2.18 times 10 to the 25 meters. So that's a bit of a trip. Stating any assumption, estimate the age of the universe in years. Okay, well, we know it's going to be 1 over this Hubble constant that they've just gave us in the formula booklet. Okay, so now if I do the reciprocal of this, I get 4.545454 times 10 to the 17. Of course, we know that's seconds. So we'll divide by 3600, we'll divide by 24, we'll divide by 365, and we get about 1.4 times 10, 1.44 times 10 to the 10 years, which, as you may know, is 14 billion. Okay? Now, what assumptions have we made? What assumptions have we made? Well, we know that this graph from which this Hubble constant or parameter is derived from kind of changes. So we're assuming it hasn't changed. We're going on the value of that. Okay, we're assuming that this constant has been unchanging since the Big Bang. Okay, we only have data and stuff to help us figure out this graph now. We don't know what happened long ago. We're assuming these recession speeds from the really, really far away galaxies have not changed. And we're assuming this is a straight line graph, something to that effect. Part B was asking about why there's a change in the wavelength. It's due to the expansion of the universe and the redshift, okay, or galaxies moving away. Now, you can't just say, oh, it's because of redshift. I said it was due to redshift because of the expanding universe, okay? Something like, or you could say, hey, the galaxy is moving away. That's probably a better way, but either way, okay? I believe that was fine for our calculation, is what we did. Okay, and yeah, we've done this calculation as well. We assumed constant recession speeds. Universe expands at a constant rate. That's a debate. Is it expanding at a decreasing rate, at an increasing rate, or at a constant rate? Different models have different theories of that. Okay, we can say it's been constant since the Big Bang. That's the assumption. One mark for the assumption, and then 2 for your calculation. This is the WJEC AS Unit 1 paper from 2017. Stars are good approximations to be black bodies. What's meant by a black body? We say black bodies are perfect emitters or absorbers of radiation. Okay, that might be one way to look at it. We'll take a look at the mark scheme in a moment. It's 1 mark. This graph shows the black body radiation for 2 stars. We've got Polaris, or the North Star, and Chi Pegasi, that's in the Pegasus constellation apparently. They are equidistant from Earth. Okay, right. Just before we do anything, and I'm just going to zoom this down a bit so we got the whole graph. Before we do anything, let's just take a look at what we see. We see that the peak wavelength for Chi Pegasi is, I don't know, around 800 nanometers. We see it's around 400 here for Polaris. All right, so that's more of a, I'm going to guess, blue tinge. Okay, so 3 things. Use the graph to state 3 differences between Polaris and Chi Pegasi. Okay, so we've been talking about this already. We know that Polaris has a much higher spectral intensity. Okay, we know that Chi Pegasi has a much higher wavelength, the peak wavelength there. Okay, and we were saying how the spectral intensity for Polaris seems to be at about 400, which is close to the blue. So that's probably going to be a blue-white color. And we know from these types of graphs before that this is more, Chi Pegasi is going to be in the more orange-red range, aren't we? I think we've covered the 3 there, haven't we? The surface temperature of Polaris, okay, how does the graph confirm this? But I suppose we could just use Wien's law, couldn't we? So if you want to do the calculation here, 400 times 10 to the negative 9 nanometers, yeah. And that's what you get when you do Wien's law, so there it's confirmed, okay. Polaris is 431 light years from Earth, and the intensity of radiation received on Earth, they tell us, show the luminosity of Polaris is approximately that many watts. Intensity is going to be our power, or our luminosity, divided by the area, isn't it? Units are watts per meter squared. So if we want to find the luminosity, we're going to take the intensity and then multiply by our surface area. The radius in this case is going to be light years. We're going to have to convert that into meters. You plug that all in. Let's see how that goes. Here we are down here. So the intensity they gave us times pi, 4 pi times 4 pi times the radius converted into meters. That's how many light years. That's the conversion squared, and that's the value they asked us to show. Okay. Previous question. Yes, we had calculated. We said it obeys Wien's law. Okay, we've got the calculation and we've done that. That's fine. Up above, we had said that the Polaris was warmer. We had said the intensity was greater. We had said it was blue-white. Did we say it was warmer? We didn't say it was warmer. We had said that its peak intensity was at a lower wavelength. So I suppose by using Wien's law, if we were to compare Polaris with Pegasi, all right, what we're saying is, hey, these things need to be equal. We know Pegasi's got a higher wavelength, therefore it must have a lower temperature. Okay, and whereas with Polaris, we had said, hey, it's got a lower wavelength, it'll have a higher temperature. So you get that from Wien's law. You can kind of intuitively guess that. I'm not sure if I said that or not, but there you go, the temperature, okay, which comes from the wavelength, okay, the intensity, and then, of course, the color. And you don't just say they're different colors. Let's not be lazy, okay? Right, and calculate the radius of Polaris. Okay, so we've got this equation here. We want to calculate the radius. We've got the luminosity that we've just done from up above. We'll plug that in down here. We'll divide that value by the sigma and the t to the power of 4. That'll give us the area. Probably while we're at it, if you want to divide by 4 pi to give us that radius squared, and then you'll take the square root of all of that, and that should give you the radius. Let's see the calculation, right? So it's the luminosity just from above. There's your sigma. There's your t to the power of 4. There's the area. That's 4. So you're going to divide by 4 pi, and if you take the square root, that's your radius. This is an A2 Unit 4 paper from WJEC 2017. We've got a planet, Kepler 186f, and it orbits the star Kepler 186. I love these names. Part 3 here, the velocity calculated is small. Yeah, it was. Explain why small velocities are difficult to measure using redshift. Well, if that's our equation there, and you've got a very small velocity, then that probably means you've got a very small redshift. And if you've got a very small redshift, that's going to be difficult to measure. That's going to be difficult to ensure you've got, and it's not going to be as obvious. I'd say something along those lines. So they've said redshift is small, or redshift is proportional to velocity, which is what we had said, or delta lambda is small, or you can show using the Doppler equation, which is what I lazily did. In real life, I'd be writing out actual sentences, wouldn't I? Okay. Small wavelength change is difficult to measure. Yeah, it's too close to the original. It's too hard to tell. You wouldn't really know how far off you are. Are you measuring an actual redshift, or are you measuring, something off because it's an anomaly and your measurements just happens to be off in this range of uncertainty?
Okay, and I've got the paper 3, section B, Astrophysics from the AQA 2018. So question 1 is about the Griffith Observatory in Los Angeles. You maybe have not ever been there, but I guarantee you have seen it at some point in your life.
on, cheer up, Eddie. You're about to make yourself a fortune.
Yeah, well, that's good, because I got a club to repair and an ulcer to plug.
Hey, boss! Here he comes!
I have an idea.
Get out! There's the alien antenna. That's where you must look to save Sergeant Suckers. If you don't, you will all become park people. And they will enter your...
Cut, let's move the camera.
Monsters have already impregnated everyone, including the CIA and the FBI. Run! Get only 20 seconds before the axis of the moon.
Hey, my turn.
Me.
Come on.
Hey, what's wrong with this picture?
Nice night for a walk, eh?
Nice night for a walk.
So very famous observatory there. Calculate the wavelength of light with which the Griffith telescope has a minimum angular resolution of 1.8 times 10 to the power of negative 6. Okay, and so we've got our Rayleigh criterion here. They told us it was 305 millimeters, so that's 0.305 meters. And I get 5.49 times 10 to the negative 7 meters. And just in case you're wondering what color that is, it's a light green. If you go a little higher, I've been saying 550 is the yellow, but it's maybe closer to 560 or 580. And if you wanted blue, you need to go down to into the 400s. Moving on, the Griffith telescope is used to observe two-point objects which subtend an angle of 1.8 times 10 to the negative 6 radians. A typical human eye has a minimum angular resolution of about 3.2 times 10 to the negative 4 radians. Calculate the focal length of the eyepiece so that the observer can just barely resolve the two objects when observing through the Griffith telescope. Okay, so you'll get from your AQA formula booklet that the magnification is the angle subtended by the image at the eye divided by the angle subtended by the object by the or at the unaided eye. So let's plug in the values. So the typical human eye was 3.4 times 10 to the negative 4. And I think you could probably imagine that in order to have a magnification, you need the one with the least negative exponent to be on top, wouldn't you? I get about 177.7 repeated, so let's say magnification is 178. You've also been given another formula, and I suppose we could have done this all at once, in which you've got the focal length of the objective lens over the focal length of the eyepiece. Now, they gave us that information as well. We are trying to find the focal length of the eyepiece. They told us the focal length up here was 5.03 meters. Okay, so we need to find the focal length of the objective piece. So we're going to have this. We're going to have the focal length that they gave us at the beginning of the question divided by this magnification we've just calculated, and I get a 0.028. So 280 millimeter focal length for your eyepiece. Let's check the marks on that. Yeah, we've done that. That's good. We could have done this all in one calculation, but whatever. That's fine. We've done it in 2 steps. That's okay. And we did say about 5.5 times 10 to the negative 7, didn't we, using the Rayleigh criterion. We've got this asteroid, Apophis. It's got a diameter of 325 meters. It's been calculated that in 2029, its distance of closest approach is going to be a mere 30,000 kilometers. The Griffith telescope may be used to view Apophis using an eyepiece calculated in question. Okay, that we've just done. Deduce whether this telescope would be suitable to obtain a detailed view of Apophis. Support an answer with your calculation. Okay, so they keep referring to the Griffith telescope. We know that its best resolution is this many radians. We were given the distance of 3 times 10 to the power 4 kilometers. Okay, and so what distance are we going to get from that? So this angle is subtended by a distance of what we're going to get here. Okay, so this is in kilometers, which means it's about 54 meters. So that means we're going to be covering 54 meters of the asteroid. And they told us that it had a diameter of 325. So if I do 54 divided by 325, what portion of this side of the asteroid are we going to be able to see? I got about it's about 1/6. It's 1.66. It's roughly 1/6 of the surface, isn't it? So deduce whether this telescope is suitable for giving a detailed view. We're going to be looking at an area covering 1/6 of this whole asteroid, which seems like a very, very big section. So I don't think we're going to get a detailed view at all. Let's see what they say. Okay, so either you can have the telescope. Okay, so this is what we did. We resolved it down. We got 54 meters, and like I said, 1/6. It's not suitable. Okay, so boom, boom, boom. Or you could use the angular. You could have calculated the angular size of the asteroid. You could have said that's the diameter. That's how far away. What's our angular resolution? Then you could have done a comparison of the angular resolution and said, hey, this is a lot bigger than what the telescope can do. As this is larger than the resolution of the telescope, the asteroid can be seen. Well, it can be seen, but I would not say in detail, and I'm not sure what they're saying with this bit here. But anyway, have a pause on the screen if you want to read what else it says there. Okay, I think we've seen this question already. Draw yourself a diagram. Okay, so we know the shape of the curve. We know it's steeper here on the left. We know it's going to kind of flatten out, be a little less steep on the right. That's generally how it should look for 2 marks. So we've done this before. Let's move on. Explain with reference to the SI units involved how the curve you have drawn can be used to determine the blackbody temperature of a star. Well, we know all about this. This is Wien's law, isn't it? Okay, we find out where the maximum intensity is, we find out what that wavelength is, and then we've got our equation, don't we? Okay, it's just going to be wavelength times the temperature is equal to a constant. So if you can figure out at what wavelength that maximum intensity is, divide it into the constant, boom, you'll get the temperature. Okay, let's just check into the mark scheme for now. Okay, so curve with a single peak, yeah, steeper on the left side, not as steep on the right side is what we said. If multiple curves are seen, they must all be correct. So if you want to gamble around with, have them inside and make the curves the right way, but I think just do one general shape, and that's probably a safer bet. Anyways, mention about the peak wavelength, quote use of Wien's law, and what the wavelength is. It's got to be in meters, and then of course you've got that formula. You can just talk about using that formula. Okay, pause the screen if you want to read the rest there. Moving on, we're going to compare stars 61 Cygnus A and 61 Cygnus B. It says they can be seen very close together. Early astronomers were unsure if the 2 stars were a binary system or if they were just in the same line of sight. So I think we're going to be asked to figure that out. Okay. So what do we got here? Okay. Evaluate whether the data supports they are a binary star system. Okay. What should we do? It says we should compare the 2 stars as seen by an observer on Earth. Okay. So that means absolute magnitude, not apparent magnitude, I would imagine. And then support your evaluation. Alright, so I've copied over the table, I've plugged some values into Stefan's law, as you can see here, and you can see that the power is a little bit larger for A. Okay, you could figure out by how much we could divide the two. If you do a ratio of power of A over power of b, I get about 1.9. You might also recall that a star of apparent magnitude 1 is meant to be 100 times brighter than 6. Okay, now if you were to work this out and take the fifth root of 100, you get an answer of 2.51. You can see this in the Wikipedia page here where they talk about this. Each star's magnitude is about 2.5 times brighter than the next faintest one. Okay, so that's because to go from magnitude of 1 to 6 is 100 times in brightness. Okay, so you've split that up. Now, if you do that, if you take a look at that, 2.51 to the power of 0.9. Now, where are we getting 0.9 from? If you take 6.1 minus 5.2, and if you were to do that to the power of 0.9, you get roughly 2.3, I believe. So this is A seems to be at least from Stefan's law, 1.9 or approximately 2 times as powerful. Okay, and you can see that the the brightness here is nearly 2 times as well. Okay, so we're trying to figure out if these stars are binary. They've got similar radii, they've got similar temperature. We can say that this one here's a little cooler. Okay, but and with their apparent magnitude being kind of similar, but when we take the radii and the temperature into account, we see that A is a little bit more powerful. Okay, so what are we trying to say with all this? Well, if it's twice as bright, then does that mean it's closer to us? Well, it could mean that if the powers or luminosities were about the same. Since we see that star A, Cygnus A, is also twice as powerful, then it means that it's twice as bright because it's twice as powerful, and has nothing to do with it being closer or B being further to Earth. And so we can kind of assume that they are, roughly the same distance from Earth, which should make them be a binary pair. All right, let's see what they say on the mark scheme here, right? So, correct calculations of power output, comparison of brightness, leading to similar distance. Okay, and therefore, yeah. So, you could say Cygnus B will be a more red, and Cygnus A is more cooler. Okay, or for me, I would assume I don't know exactly what the color level is for these. If this is a thing you need to know in AQA, good for you. But you can see they're in the orange range, but of course the cooler one will be closer to being red. Okay. Don't worry about calculating, doing anything with the wavelength unless you use it to link exactly what the color is. But I think there's more important things to do. Okay, we've compared the brightness. As I said, they've got this difference in magnitude, and then from there you can figure out what the ratio in brightness is. They say it's 2 times as bright because the apparent magnitude is about 1 less, right? Yeah. 0.9. So if it's 1 less, it's supposed to be about 2.5 times brighter. I mean, you don't even really need to do the calculation, but there it is. When you plug into Stefan's law, you get, again, like I said, it is about twice as bright. And just the last bit, we've said they have to be about the same distance away, and so you can say, therefore, yeah, they're a binary system, which we did. What's the spectral class for Cygnus A? I think we just saw it's going to be K, didn't we? Because it's going to be in that range there. Okay? Something apparently you need to know in AQA. Describe the links between galaxies, black holes, and quasars. Okay, so we saw a quasar is a quasi-stellar object. They tend to be at the center of galaxies, near black holes. It's a big accumulation of gas, which is being pulled into the black hole, and it gives off a great amount of energy. I'm not sure what else they're looking for, as I'm not too familiar with this side of the AQA course. Let's move on and take a look at this calculation here. They want us to estimate the age of the universe in seconds. They've given us the redshift of a star, Markarian 231. Okay, so we can do that calculation. All right, so we'll recall that our Z, our redshift there, okay, that's going to be a V over C. Right, so we know V is equal to CZ. We also know that should be equal to Hubble's constant times the distance. Now, it's that many light years, so we're going to have to convert how many light years that is into meters. All right? Right, and what is that conversion factor? It's about 9.47, I think, in this exam board they tell you. It's that many times times 10 to the 15. It's that many meters. Okay, so we want to get an age of the universe. Okay, so we're going to solve for... since we know the inverse of the Hubble constant is the age, should we just write out solve for 1 over h? I think that's fine. I'm going to bring my h naught down there. I'm going to have d here, and let's plug in the numbers. So 5.81 times 10 to the 8. Okay, it's that many light years times the correction factor, and then we're gonna have the ZC slip underneath. Okay, so Z, that's nice and simple, and then times R3 times 10 to the power of 8. Watch your buttons on your calculator with this sort of thing. Get it all in a bracket, or make sure you're using your exponent button. But if I do this, I get 4.42 times 10 to the power of 17. If we divide by 86,400, that'll tell us how many days. I'll divide that by 365, and I get 1.4 times 10 to the power of 10, or in other words, 14 billion years. And that seems consistent with what we seem to think is the age of the universe. Last part of number 3 here. A typical quasar is believed to be approximately the size of our solar system, and it's got a power output of about 1,000 galaxies. Estimate, with reference to the inverse square law, how much further the most distant visible quasar is likely to be compared to the most distant visible galaxy. Okay, well, inverse square law, we know that the intensity is going to diminish. It's to do with the inverse, the square of the distance. Okay? Okay, so here's our inverse square law. This is what we're saying. Now, if this thing gives off 1,000 more, let's do it like this, okay? Let's talk about the power of the quasar, the power of the galaxy, okay? And what we can do, if it's just barely good enough for us to see, the intensities here are equal, aren't they? Okay? And I think we know intensity is power divided by this radius squared. I've got this set up here. Now we know that the power of the quasar is equal to 1,000 normal galaxies. So we've got that. And if we want to look at the ratio in distance, the ratio in distance is going to be the square root of 1,000. And we're looking at a little over 30, aren't we? Yeah, so it's about 31.6. I would say that that means that the quasar can be probably about almost 32 times further away. We can still see it because it's so powerful. Even with the inverse square law, we'll be able to just barely see it. That's the way I would look at that question. Let's go have a look at the answers. Okay, so quasars are produced by supermassive black holes, and these black holes are at the center of active galaxies. Okay, little different than what we had seen about quasars in a previous question, but you AQA crowd, you know what you need to know, I hope. Okay, I've got the answer that they've got here. There's different ways you could do this, right? They've got you calculating V separately. Okay, that's fine. They've got it in kilometers per second, and then they're changing. They've got a parsec is how many light years, and they're taking this distance in light years. They're changing it into parsecs so that you can come up with this many parsecs, and then they're coming up with. I guess you divide the two so you can get their h value is 70 kilometer per second per megaparsec. You flip that over, and now they're changing that distance into the light years into meters, and they're getting into the seconds. So, I mean, it seems a bit silly to go for this whole unit with the megaparsec. I mean, for me, doing it all at once in one calculation makes sense to me, but you do it how you like. We got it to work out. And this is a good question, because you know it's going to be, 13, 14 billion years. You should know that. Okay? Pause if you want to read more on the right there. And what did we say about the quasar and the galaxy? They have the same brightness because they're both that they're just at the limit of what we can perceive. Okay, inverse square law, the power divided by the square of the distance. Yeah, actually, they've set up a ratio just like I've done, and they end up with that 1,000. So that's how we got the 30. We've done it just the same. That's fine. Again, have a look on the right there if you like. Okay, I've got another cosmology question. We haven't seen too many Big Bang ones. We've got evidence to support the Big Bang comes from cosmological microwave background radiation and the relative abundance of hydrogen and helium. What is meant by CMBR, and how does its existence support the Big Bang theory? Okay, well, this radiation is all around us. We know that it came from gamma radiation, which has been stretched out over time because of this expansion. At least that's what we think, and at least it supports that idea, because if there were to be a Big Bang, we would have a massive explosion with lots of radiation, with high energy being given out. Okay, it would have been a tremendously hot, a lot of heat, a lot of energy, and over time that's cooled down. I think we've seen in other questions that the temperature of the universe in general is very close to 3 Kelvin, because if you were to plug in, that energy is proportional to the frequency. So if you've got a very stretched out wavelength, that's going to be a smaller frequency, which is going to mean a lower energy. So they've said here radiation coming from all parts of the universe. Yeah, that's what it is. The radiation's been redshifted into the microwave region. That's kind of what I'm looking at. This is something I've not seen in other courses, but they say when the universe cooled sufficiently for matter and radiation to decouple the combination of protons and electrons to neutral atoms. Okay, getting into a little more particle physics than I'm used to. That's fine. The other thing you could have said is that this EM radiation's all over the place. Okay, so either way, that's fine. It's from all parts. And the spectrum has a peak microwave region. It corresponds to, like we said, just below 3 Kelvin. It can be interpreted as radiation left over from the Big Bang, and the photons have been stretched, and they give lower energies. I think I've said that. Do you know that? Can you formulate that into a nice little paragraph of a few sentences? And the last bit, the other bit, I was wondering if they were going to cover this. Explain how the relative abundance of hydrogen and helium supports the Big Bang theory. Okay. Now, we know that most stars are made of hydrogen and helium. I mean, all stars are. And we know that hydrogen fuses into helium. But how does the abundance of hydrogen and helium support the Big Bang theory? I'm not very versed on this one, so let's just jump to the marks. They say the Big Bang theory suggests a brief of fusion occurred, resulting from the production of helium from fusing hydrogen. I didn't think that hydrogen atoms had existed and could be fused during the Big Bang. But here we go. That's fine, because they're talking up above about combinations of protons and electrons. You're not going to have that happening before. You're not going to have fusion of hydrogen happening before that. But anyway, fusion stopped as the universe expanded and cooled. Yeah, I suppose at the very beginning you would have had some fusion happening, but then as the universe expanded and moved apart, we wouldn't have that anymore. It's like having the reverse conditions for a star to be formed, I suppose. Resulting in relative abundance of helium and hydrogen. Cool. Yeah. Okay. I've never heard this argument before. That's kind of a new one, so I hope that makes sense to you, and I hope you can get those marks. Okay, and here we've got a paper 3 from Cambridge Pre-U. Okay, so calculate the speed of recession. So c times, what is our difference at 137.6 over what it would be in the laboratory? Okay, so we get, let's say, 8.5 times 10 to the 7 meters per second. If you get something above the speed of light, something is wrong. Right, state Hubble's law. Hubble's law, we've actually done this before already, but I think that was 1 mark. This is now 2 marks. So Hubble's law tells us that the further away the galaxies are, the greater their recession speed, and that's because the greater the redshift, something to that effect. Let's see what they say. Recession of the galaxy is directly proportional to its distance. Good, okay, that's what we had said. Before, that was 1 mark. Now it's 2 marks. Okay, you could say this equation with the symbols explained. Okay, that's interesting. And there's our answer from before, so we're all correct there. Explain how redshift leads to the ideas of the expanding universe and the Big Bang theory. Okay, it's 4 marks here. I would probably dedicate 2 marks to talking about how that means that the universe is expanding, and then 2 marks to talking about Big Bang Theory.
Not a great plan.
Or the other thing you could do, actually, might be to, first of all, explain what the Big Bang Theory is, and then talk about how redshift leads to the idea of the expanding universe, which helps explain the Big Bang Theory. We know the greater the redshift, the greater the speed of recession. So we've also noticed that the galaxies that are moving really, really fast are the ones which are furthest away. And if we trace things back, we can get back to that point. Okay, but what this tells us is that the galaxies which are fairly close to us are moving away. The ones which are even further away are moving faster. Something doesn't just move fast because it's moving a certain distance in the same amount of time in this case. Okay, what's happening is the time of the universe hasn't changed, but this distance has increased because the universe is actually expanding. That might be a way you could think about, well, why is it moving faster when it's further away? Well, because it's been stretched. You can think of it that way, maybe, if that helps. So let's take a look at what they've said here. The unique point at which space and matter all started, that's the Big Bang. Just explained that everything was concentrated at one point, and then you could say any of these, okay? Everything's moving away from everything else, then space is increasing, okay? The idea is that space is increasing, not that space was already there. So the actual space is expanding outwards, okay? The future of the universe can in theory, be programmed when computer works backwards in time. All galaxies get closer and closer. Space shrinks when we work backwards. I mean, I don't see how we've even talked about redshift here. I've seen Mark schemes explain this better. This one's kind of vague compared to other ones I've seen.
Yeah, well, that's just like your opinion, man.
Anyway, let's look at part D. The Hubble constant has this estimated value, estimate the age of the universe. It's just 1 over. It's just the reciprocal is all you need to do. Just say, hey, the age of the universe is a reciprocal of the Hubble constant, and there we go. Okay?
Right, here we are, another binary star question. This is from OCR, the Unified Physics, which is a paper 3 of the Physics A. Stars are viewed from Earth in the plane of rotation. Stars are observed using light that has a wavelength of 656 nanometers. The observed light is shifted. Calculate the maximum change observed. Okay. So this is going to be, we're going to swing this up times our ratio of our speed of light there. The question remains, what is the velocity? What is it? Our velocity is just going to be that circumference divided by the period there. Right? So they gave us that radius, they told us the period, and there we go. So I got a velocity of 63,853 kilometers, well, I'm guessing meters per second. My shift is 0.14 nanometers, I believe. Let's check how we're doing so far. 0.14. Okay, one more question about Wien's law, it seems. We've got a comparison of Sirius A and Canopus. And again, it's the same type thing. Confirm that Wien's displacement law is valid for the stars. Just in the interest of time, I think we know what we need to do here.
Because of the time.
Time is what he's indicating there.
Right, you're going to have theta 1 T1 equals theta 2 T2. Okay, and just compare the two, right? You've got your peak wavelengths there, you've got the temperatures they gave, so you're just going to read them off the graph, you're going to plug them in, and it should work out. What do they have here? So we read these wavelengths off the graph, attempt at applying Tmax, right, to both stars. I would have set them equal to each other to do left side, right side comparison, but if you want to do it for each star, that's fine. No need to change units, correct application, other correct calculations, like I said, set them equal to each other, that kind of thing. Application of Wien's law to one star only gets 1 mark. You need to do both. Astronomers state that one of the stars appears bluer than the other. Explain how the spectra support this statement and which star would appear bluer. Right, so, well, we see here that for Sirius A, its peak wavelength is around the 350, and that's in the blue region, nanometers, so that's fine. And we would say that's the one that's going to appear bluer. Part B here, the radius of Canopus they give, and they give the radius for Sirius A. Show that the luminosity of Canopus is approximately 500 times. Okay, well, here's what we'll do. We'll do luminosity of Canopus over luminosity of Sirius A. The sigmas will cancel. The 4 pi's will cancel from Stefan's law. We'll have r squared, and we'll have t to the power of 4. If we plug in the radii that they've given us, square them, and if we use the temperatures from the graph up above and take them to the power of 4, we should get that ratio. It looks to me like they're going in and calculating them separately, getting separate answers, and then dividing. I think it's nice and simple to set it up one time, one calculation, and then you've got it, and it ends up being about 500. Let's scroll back up to what we were talking about before. Sirius A, greater spectral intensity at the blue end, close to the 400. Don't accept peak wavelength is closest to blue end of spectrum than Canopus. That's interesting. Don't accept reference to temperature by itself, because we know higher is bluer. We can't say that. Accept a ratio for both stars, but this is interesting. Don't accept peak wavelength of Sirius is closer to the blue end of the spectrum. That's not good enough. You need to say Sirius A has its intensity, the greater spectral intensity at blue end, or at shorter wavelengths. Yeah, that's what we had said. Interesting, the stuff they won't accept, so just watch that. Okay, a couple more questions. Calculate the intensity of radiation reaching the surface of the Earth from Sirius A. Told us the distance from the Earth, so that's what you're going to substitute in for the R here. And you've got your luminosity from up above, and there's your calculation. The intensity of the radiation reaching the Earth's surface from Canopus is less than that of Sirius. Yeah. Even though Canopus has a greater luminosity. Explain this contradiction. Well, it probably is that Canopus is further away from the Earth than Sirius is, so it's got a greater luminosity, but it's further away. And maybe mention something about inverse square law and talk about the further away, that sort of thing. The square of the distance is going to cause a drop in the intensity. Okay? Yeah, Canopus is further away from Earth, or you can say Sirius A is closer. You can talk about intensity reaching the Earth. There we said. Good, inversely proportional to the area, or at least to the r squared. Don't accept intensities inversely proportional to distance. Or because of inverse square. Well, you can't just say, inverse square law. You have to say, it's inversely proportional to the radius, the distance between the things. And that is the inverse square law, isn't it? But they want the details here. They're not accepting lazy answers in the WJEC, are they? Okay? And then that calculation up above, like they say, they give that to us, you plug in the stuff from before, and you get your answer. Okay? Some pretty simple calculations here.
Okay, and that takes us up to an hour. That's all we've got time for, and I hope that was helpful. Practice your written work, practice your calculations, and we'll see you in the next one. Thank you.